Hello everyone, welcome to my YouTube channel. So today I am going to discuss an interesting problem from linear algebra. This problem is from the CMI 2024 subjective paper. Okay, and this problem is very important for JAM aspirants as well as NET and GATE aspirants because this is very nice and interesting problem. So let P be a prime number and let n greater equal to 2 be an integer and V is a n-dimensional FP vector space. What do I mean by that? So FP, so solution, let's change the ink. So FP is a field with P elements, okay, filled with P elements, and so V is a n-dimensional FP vector space. And we need to find number of two-dimensional subspace of V. Okay, this is the question. First I will calculate the number of two-dimensional subspace, then I will do for general number of k-dimensional subspace. Okay, so V is a n-dimensional FP vector space. So observe that if you want to uh, count the number of subspace of two-dimensional, then you need to find first the possible basis for it, right? Because a subspace is completely determined by its basis. Okay, so that means let W be a two-dimensional subspace. Okay, W be a two-dimensional subspace, then W is span of x and y, two vectors where x and y are linearly independent. So my first goal is to count this possible basis. Okay, because if you find the basis with two elements x and y are linearly independent, then it will span a two-dimensional subspace, right? So how do I calculate it? So how can you choose x here? So first of all, x must be a non-zero vector, right? X must be a non-zero vector. Why? Because if x is a zero vector, then it cannot then W is not a two-dimensional subspace, right? So x must be a non-zero vector. So how many non-zero vector can you find from V? So first, before going to compute this, we know any two n-dimensional Vs are isomorphic, and dimension of V is n, right? So that will imply V is isomorphic to Fp power n, right? So that means cardinality of V is same as cardinality of Fp power n, which is same as P power n, right? So cardinality of V is P power n. So since x must be a non-zero vector, so choice of x equal to P power n minus 1, right? So choice of x is P power n minus 1, because 0 we can't choose 0. So choice of x is P power n minus 1. Now we need to choose y. So how can we choose y? You can choose any vector y which is not linearly dependent with x. Now y is linearly dependent to x if and only if y equal to some c times x, where c belongs to Fp, right? So y is linearly dependent to x if and only if y equal to c times x, where c belongs to Fp. So choice of y such that y is linearly dependent to x equal to p, because you can vary c, you can take any c from fp, you can take ax, 2x, 3x up to p minus 1x and 0, and these all vectors are linearly dependent to x, and if you choose any other vectors, that must be linearly independent with x, because y is linearly dependent to x if and only if y equal to some constant times x, some scalar multiple of x, and the scalar comes from the field, and here the cardinality of field is p, because field is fp itself. So cardinality of field is p. So choice of y such that y is linearly dependent to x is p. So then choice of y such that y is linearly independent to x equal to p power n minus p, because we remove these p many vectors which are linearly dependent to x, and then outside of this vectors set, if we choose any y, then that must be linearly independent with x, right? So that means this is the choice. So hence this choice of this set, choice of basis equal to p power n minus 1 times p power n minus p power n minus p power n minus 1 times p power n minus p. But here is a problem. Where is the problem? That you can see that there are two different bases that can generate the same space. Like as an example, take an example. You can take example from anywhere. So take example, say in R2. R2 is two-dimensional VS. If you take 1 0 and 0 1, this is also spanned by R. This also spans R2, right? Also, if you take R2 to be say span of, can take 1 comma 1 and say 2 comma 1, this also spans R2. That means for different choice of bases you can get same subspace. So that's why we need to find that how many different bases gives me a same subspace. Okay, then how do I calculate it? Let so let W equal to span of xy, and which is same as span of u comma v. Then u equal to, u belongs to span of x comma y, then u equal to c1x plus c2y, where c1 c2 belongs to fp. Okay, and v belongs to span of x comma y, where v equal to say d1x plus d2y, where d1 d2 belongs to fp. Okay, then what will happen? Now we need to calculate the choice of c1 c2 d1 d2. Okay, so observe, choice of c1 is p, choice of c2 is p manis. But if you choose, so that means total choice equal to p square. But there is a problem. Why? If you choose c1 equal to c2 equal to 0, then u becomes 0. But I already assumed that W is a span of, W is a two-dimensional subspace which is spanned by u and v. That means u and v both are non-zero, right? So that means here the choice must be, we can't take c1 and c2 both to be 0 at a time. So total choice equal to p square minus 1. So this is for this one. Now what is V? Since W is a span of U and V, that means, and W is a two-dimensional subspace, that means U and V are linearly independent, because U and V, this set forms a basis for W. That means V must be linearly independent to U. So by similar argument, for V also we can choose D to be P many and D2 to be P many. So total choice P square. But again there is a problem, that since U and V are linearly independent, so we need to exclude some possible choice of D1, D2. When it becomes linearly dependent with U, we need to exclude that cases also. So V is, say, linearly dependent with U, that will imply V is linearly dependent with U, that will imply V equal to lambda times U, where lambda belongs to Fp. Fine. So that means if I want to find the possible choice of V where V is linearly independent with U, that means we need to exclude these cases, right? So again, the total choice equal to, so for U we have P square many choice because of this C1, C2, and then we exclude 0 here, okay? And since V is lambda times U, so, and lambda belongs to Fp, so that means we need to exclude P many choice from here. So that's why we get P square minus P, okay? And in this P many choice we already exclude 0, because we can take lambda to be 0 and then V becomes 0. So we already exclude the case of zeros here, okay? So that means, so hence the actual choice becomes P square minus 1 times P square minus P, okay? So if you particularly, or if you fix a basis for some subspace W, X and Y, then there are P square minus 1 times P square minus P, this number of different bases which spans the same subspace. So since we are calculating number of distinct subspaces, so since we are calculating number of distinct subspaces, so for each fixed basis, these many different bases also spans the same two-dimensional subspace. So since we are calculating number of distinct subspaces, this cardinality, this becomes P power n minus 1 times P power n minus P divided by P square minus 1 times P square minus P, because this many choice gives me the same basis, this many choice gives me one basis. So that's why distinct, if I want to find this distinct number of subspaces, we'll have this, okay? So this is for two-dimensional. Now by same argument, same proof, we can find k-dimensional subspaces. So how do we do that? See, here we are taking that X must be a non-zero vector as a first vector, right? So that means choice of X is P power n minus 1. Then we find choice of Y. Choice of Y is P power n minus P, right? Now if I take another Z which is linearly dependent, okay, suppose it is 3. For 3, say it is X, Y, Z. Then how do you do that? For X, you have P square minus Y. For Y, you have P square minus P, that we have already shown. For Z, if Z is linearly dependent, to this set X and Y, then Z equal to C1X plus C2Y. And choice of C1 is P, choice of C2 is P. So that means you need to exclude, here it is not p square, it is p power n, sorry, p power n minus 1 and p power n minus p. So that means if z is linearly independent to xy, we need to exclude this case. So that means choice of z equal to p power n minus p square. Similarly, if there is another extra vector, if it is not three-dimensional, if it is four-dimensional, there is some w, and for w we will get p power n minus pq, and so on. This is the first case, right? And similarly, here if we want to divide it, okay, the same condition, here we are trying to start with the two-dimensional subspace, but if it is k-dimensional subspace, so we will start by the same definition, that if w is span of x1 x2 up to say xk, and which is same as span of y1 up y2 up to yk, then first choice of y1 equal to c1 x1 plus c2 x2 plus dot 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 ck xk. So that means you need to remove, uh, so that means you need to remove, you have p power k many choice, and you need to remove first one vector because you first exclude 0, and similarly the other vectors. So that means you will get the answer. So this is homework to find, to solve, to write the proper proof for general k dimensional subspace, which is same as this. Okay, that is, the answer is answer equal to, so it is p power n minus 1 times p power n minus p dot 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 p power n minus p power k minus 1 by p power k minus 1 p power k minus p dot 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 p power k minus p power k minus 1. This is the answer. So this is number of k dimensional, distinct k dimensional subspace of a n dimensional vector space over the field fp. Okay, and the proof is same as we have done for 2. In CMI 2024, they just ask for two-dimensional subspace. Okay, this is a very important problem. Okay, so I hope you like this video. So please, if you have any doubt, please comment below. I will definitely answer. Thank you.